Welcome back. Okay, we are continuing with that factors influencing solubility of solid in a liquid that we completed now. Now next is gas in liquid. Solubility factors influencing solubility of gas in liquid. Two factors are there. One is nature of gas. The other one is three factors are there: nature of gas, temperature, and pressure. Nature of gas. Look at that. Look at the monitor. Nature of gas, temperature, and pressure. Nature of gas. Easily liquefiable gases are more soluble in solvents, in liquids. One more thing, gases which can undergo chemical reaction with the liquid, they are also easily soluble. Polar gases are easily soluble in water. Okay, only that much regarding nature of gases. Then temperature, that is also very easy to understand. Dissolving of gas in liquid is like condensation. Contraction in volume takes place. When there is contraction in volume, energy will be released. So, dissolution of gas in a liquid we are considering as contraction. Condensation, there is contraction. So, we are considering it as a condensation process, and hence this process is exothermic, energy is released. Since the process is exothermic, when we increase the temperature, what happens? Solubility decreases. The next and the most important point we have to study is, now see the board. Effect of pressure on solubility of gases. Effect of pressure on solubility of gases, given by Henry's law. Effect of pressure on solubility of gases. According to this Henry's law, 1 second, you see that monitor. What is the effect of pressure on solubility of gases in liquid? See the monitor. What is the effect of pressure on solubility of gases? Look at the monitor. Two diagrams are there. The white portion of that first as well as the second container represents liquid, and the blue portion represents gas. Black dots are the gas molecules. W1, that represents the pressure. W1, W2, W3, etc. that also denotes what? Pressure. Look at the first diagram. When the pressure is low above the gas, that is above the liquid, the number of molecules which has dissolved in that liquid, and also see the amount of the number of gas molecules which dissolved when the pressure is increased. Definitely the number of gas molecules dissolved will be more when the pressure is increased. The number of gas molecules dissolved will be more when the pressure is increased. Okay, now look here. So, look at the board. Pressure of the gas above a liquid is pressure of gas above a liquid is directly proportional to the solubility of the gas. Solubility of the gas in the liquid. Henry suggested like this: pressure of the gas above a liquid is directly proportional to the solubility of the gas in the liquid. Same time only the other scientist Dalton was there. He said instead of pressure we have to use what? Partial pressure we have to use. So, he changed the term pressure. Instead of that, he also used partial pressure of the gas above the liquid is directly proportional to the solubility of the gas in the liquid. Again, solubility of the gas in the liquid means concentration of the gas in the liquid. So many concentration terms we have. Out of that, molarity, mole fraction, etc. are there. They mathematical calculations they did, and they found out that partial pressure of the gas above the liquid is directly proportional to the mole fraction of the gas in the solution. So, solubility of the gas in the liquid is denoted by which concentration? Denoted by mole fraction. Partial pressure of the gas above a liquid is directly proportional to the mole fraction of the gas in the solution. Okay. So, P gas is proportional to X gas. P gas is equal to a constant KH into X gas, where KH is known as Henry's law constant. We know that X is the mole fraction. Mole fraction of the gas is equal to number of moles of the gas divided by number of moles of the gas plus number of moles of the solvent. In most of the cases, solvent will be water. There we will write number of moles of H2O, NH2O. X gas is equal to N gas divided by N gas plus number of moles of the solvent. And also we know that the number of moles of the gas dissolved in the liquid will be very less. Therefore, for doing calculations, we will neglect that N gas in the denominator, and finally we will write P gas is equal to KH into N gas, number of moles of the gas divided by number of moles of the solvent. Okay. So, this is the mathematical relationship showing what Henry's law, that gives us what? Gives us the solubility of a gas in a liquid. Partial pressure of the gas is directly proportional to the solubility of the gas in the liquid. That solubility is denoted in terms of mole fraction. So, P proportional to X, that is X of the gas, then P gas is equal to KH into X gas. This is Henry's law, and based on this, so many applications are there for Henry's law, and let us see what type of questions are coming from this. Applications, what when I say applications, applications of two types of industrial applications are there, as well as for so many biological phenomena we can explain by using this Henry's law. Okay. Now we will see the questions based on this Henry's law. Only application questions I am going to show you. Look at the monitor, see the questions given there. Applications of Henry's law, those applications are given as questions. There is a graph over there, that graph you can see, that graph, this same thing only, P gas is equal to KH X gas, that is when you plot partial pressure of the gas against mole fraction of the gas, you will get a straight line, because in 12th standard so many graphs you are studying, in all those graphs are the graphs of straight line only, in the form y is equal to mx plus c. Okay. P gas corresponds to the y axis and X gas corresponds to the x axis. So, when you plot C is equal to 0, y intercept is equal to 0. So, the graph will pass through the origin and the slope is equal to what? KH. Okay. Now, let us see the question. Give reason. At higher altitude, people suffer from a disease called anoxia. What do you mean by anoxia? Breathlessness, incapable of thinking properly. Such things, it's known as anoxia. Why? What is the reason for this? This is because at higher altitude, partial pressure of oxygen is less. So, the amount of oxygen dissolved in the blood will be less. That is why when you climb, if you want to climb mountains, what you have to do? You have to take one oxygen cylinder with you. Otherwise, what happens? Breathlessness or what? That weakness, all these things you will feel. Okay. So, that is what is anoxia. The answer is, what is the answer? Partial pressure of oxygen at higher altitude will be less. As a result, the amount of oxygen present in the blood will be less. Now, look at the second question. Aquatic species are more comfortable in cold water. Already we have seen solubility of gas is directly proportional to, not directly proportional, solubility of gases decreases with increase in temperature. So, definitely you got the answer. Aquatic species are more comfortable in cold water, because only in cold water the amount of oxygen present will be more. In hot water that much amount of oxygen is not there. Now, there is a problem based on this Henry's law. We will see the problem afterwards. Just see the next question. H2 is more soluble in water than He at a given temperature. Which one has higher KH? H2 is more soluble in water than He at a given temperature. Which one has higher KH and why? For that, we have to see this equation. Partial pressure P gas is equal to KH into X gas. So, from this relation, we know that KH, from this relation, we know that KH is proportional to 1 by Xg. That means, this represents what? X represents, that is the mole fraction of the gas in the liquid. It represents the solubility of the gas in the liquid. So, what is the relationship between KH and Xg? When KH increases, solubility of the gas decreases. Now, say the answer. When KH increases, solubility of the gas decreases. H2 is more soluble, means it has lower value of KH than He. Which one has higher KH? Which one has higher KH? HE has higher KH because this is the reason. KH is proportional to 1 by Xg. More the solubility, lower will be the value of KH, or higher the solubility, lower will be the value of KH. Okay, so that is the answer. Now let us see the problem over there. One problem is there, Henry's law constant problem is there. Look at that problem. See the monitor, look at that problem. Henry's law constant for carbon dioxide is 1.67 into 10 raised to 8 pascals at 298 Kelvin. So KH is given there. Just see the question, after that we will see the board. Calculate the quantity of CO2 in 500 ml of soda water when packed under 2.5 atmosphere pressure. So partial KH is given, partial pressure of the gas is the, let me see, write the data, after that you can see the monitor. 2.5 into 10 raised to 5 pascals, the other one 1.67 into 10 raised to 8 pascals. Okay, now see the board. So KH value is given there, and partial pressure of the gas is given there. We have the equation, partial pressure of the gas is equal to KH into X of the gas. By substituting these two values in this relationship, what you can find out? We can find out X of the gas, that is mole fraction of the gas you can find out. Substitution part I am not going to write. X of the gas is equal to partial pressure of the gas by KH, and that answer is equal to, answer I will write because then only we can proceed with the problem. 1.5 into 10 raised to minus 3. So mole fraction of the gas is equal to 1.5 into 10 raised to minus 3. Okay, question is not that, question is not to calculate the mole fraction of the gas, question is to calculate what? Question is to calculate the quantity of CO2 in 500 ml of soda water. Okay, again look at the board. Xg is equal to number of moles of the gas divided by number of moles of the gas plus number of moles of the solvent. Okay, number of moles of the gas divided by number of moles of the solvent. We don't know the number of moles of the gas, so number of moles of the gas, that is carbon dioxide gas, divided by, in the denominator this number of moles of the gas is very small compared to the number of moles of the solvent. So neglect this number of moles of the gas in the denominator, it becomes equal to number of moles of the solvent, that is equal to number of moles of the gas divided by number of moles of the solvent. What is number of moles? That is equal to W by M. What is W by M? 500 divided by 18. What is 18? 18 is the molar mass of water. Okay, 500 divided by 18. So when you substitute 1.5 into 10 raised to minus 3 is equal to Ng, number of moles of carbon dioxide divided by 500 divided by 18. Okay, 500 ml will be equal to 500 grams because 1 gram per ml is the density of water. So from this what you can calculate? You can calculate number of moles of carbon dioxide from this Ng, that is number of moles of carbon dioxide. You can calculate that number of moles of carbon dioxide is equal to, when you calculate number of moles of carbon dioxide, that answer will be equal to, number of moles of carbon dioxide is equal to, again I will write the answer, otherwise we cannot continue easily with this problem, 0.0422 mole. This is the number of moles of carbon dioxide. Okay, this is the number of moles of carbon dioxide. Again it is not over. Question is again what? Calculate the quantity of CO2. They are not asking the number of moles of CO2, the quantity of CO2 means the mass of CO2. The mass of CO2 they are asking. We know number of moles of CO2 is equal to mass divided by molar mass. Therefore, what we have to do? Mass of CO2 is equal to number of moles of CO2 into molar mass of CO2. Molar mass of CO2. So, 0.0422 into 44. This much grams you will get. Okay. Final answer we can find out. This is the, otherwise all direct questions will come. Here the only indirect portion is, instead of giving per liter of water, if it is given CO2 dissolved per liter, we take it as number of moles of the solvent we take as 55.55. N solvent directly we will take as 55.55. Here instead of giving number of carbon dioxide dissolved per liter of the solvent, what is given, the carbon dioxide is dissolved in 500 ml of the liquid, 500 ml of water. That is the difference in this problem. Otherwise there is it's not at all difficult, and not only that, they are not asking the number of moles of carbon dioxide, they are asking the mass of carbon dioxide. So you have to do one more step over here. Okay, so this is what is factors influencing solubility in that Henry's law. That is the most important portion that I think you understood. Okay, now let us see what is next. Next is vapor pressure of liquid in liquid solutions. Next is a very important topic, vapor pressure. Vapor pressure. You know what is vapor pressure? The pressure exerted, the plain definition of vapor pressure is pressure exerted by vapor above a liquid in equilibrium with the liquid. That is what is vapor pressure. Now what is the meaning of that? Suppose we have a beaker like this, we have liquid over here. Okay, close this beaker. What happens? We know that these molecules are in motion, they collide with each other. The molecule having higher kinetic energy have the tendency to escape into this, into the vapor phase. So that molecule will escape into this vapor phase. That is what is known as evaporation. Molecule having slightly higher kinetic energy will escape into the vapor phase. That process is called evaporation. Evaporation. When enough number of molecules are there in this space, again what happens? They also have different kinetic energies. Out of these various molecules, they also start colliding each other. Molecule which is having lower kinetic energy will come back to the liquid. That is what is known as condensation. Initially there is only evaporation. After some time what also will take place? Condensation also will take place. Condensation also will take place. And a stage will be reached. What is that stage? Rate of evaporation becomes equal to rate of condensation. That particular stage is known as equilibrium stage. How can you understand equilibrium stage is reached? You connect this with a pressure reading meter, manometer or something. Okay, there are instruments for measuring the vapor pressure of the liquid, vapor pressure of the vapor above this liquid. Connect it with a pressure reading, pressure gauge. You connect it with a pressure gauge. When the pressure in that pressure gauge remains steady, we can say what? Equilibrium has reached. Means rate of evaporation becomes equal to rate of condensation. Okay, so every liquid has its vapor pressure. The vapor pressure of a liquid depends upon temperature of the liquid, then nature of the liquid, surface area of the liquid, etc. Various factors are influencing the vapor pressure. Our lesson is not regarding simple liquids, we are studying about solutions. So what we are going to study? We are going to study vapor pressure of solutions, not simple liquids. Okay, we are going to study vapor pressure of solutions, vapor pressure of liquid in liquid solution, and vapor pressure of solid in liquid solution we are going to study. It's a very important topic. You may be remembering Rolle's law that you studied in this first term, you studied that Rolle's law. That is what we are going to study again. Vapor pressure of liquid in liquid solution and solid in liquid solution. Okay, once again we have a short break. Stay tuned.